about the size of the nucleus, okay, about the density of the nucleus, okay, stability of the nucleus. So different elements, the different element have nucleus. So we will see in this chapter how the stability changes, how the stability of the nucleus changes with respect to the element. Okay, for different element, there will be the different stability of the nucleus that we are going to study in this chapter. So first thing in this chapter is, first we will understand what is the structure of the nucleus. What is the structure of nucleus? So before that, we should know what is the structure of atom. So earlier I told you about the atom. The last chapter was the atom. So in that chapter we studied the structure of the atom. So basically, once again I am telling what is the atom and what is the structure of the atom. So basically, this is the atom. We are considering the atom as a spherical, okay, and at the center there is a positively charged nucleus. At the center there is a positively charged nucleus, and in the chapter atom, we studied the Rutherford's alpha scattering experiment. So from there was the discovery of the nucleus. So basically, discovery of the nucleus goes to Rutherford. So, so in an atom, nucleus is at the center, and nucleus is having a positive charge, and electron revolves around the nucleus. Okay. Now, this nucleus uh, is in the center of the atom. So we consider that the entire mass of the atom, is the mass of the nucleus. An entire positive charge of the nucleus is the positive charge of the nucleus. So entire mass and the positive charge of an atom is concentrated into very small volume called nucleus. So basically nucleus have very small volume. So and the entire charge and the entire mass of the atom is concentrated in the nucleus. You can see here radius of the nucleus, radius of the atom is 10 to the power 10 meter. When you will calculate the radius of the atom, it will come out to be 10 to the power minus 10 meter. On the other way, when you will calculate the radius of the nucleus, it will come out to be uh, 10 to the power minus 14 to 10 to the power minus 15. Okay, so it will be approximately, you can say, it will be in between 10 to the power minus 14 to 10 to the power minus 15. Now you can see here the size of the atom is much bigger than the size of the nucleus. Size of the atom is 10 to the power 4 or 10 to the power 5 times greater than the size of the nucleus. If with example we compare this size, so I am sitting in a room, okay, I am sitting in this room, and this is the tip of my pen. So if tip of my pen is the nucleus, this room is the atom. If tip of my pen is nucleus, this room is the atom. So now you can observe and you can understand that nucleus is much bigger in size as compared to, no, atom is much bigger in size as compared to nucleus. Okay. Now nuclear structure. So basically inside the nucleus there are protons and neutrons, and the protons and neutrons are known as nucleons. Nucleus is made up of neutrons and protons, and these are known as nucleons. Now what is proton? Charge on proton, charge on proton is same as that of charge on electron, but charge on proton is positive, that is plus 1.6 into 10 to the power minus 19 coulomb. Now mass of proton, mass of one proton, 1.6726 into 10 to the power minus 27 kg, and this is also equal to 1 AMU, atomic mass unit. AMU. AMU is the unit of atomic mass, unit of mass, you can say. And this 1 AMU can be represented by 1 mu also. Okay. Now, basically, what is a proton? What is a proton? If you take a hydrogen nucleus, hydrogen have the atomic number 1. Hydrogen have the 1 atomic number. Okay. And mass number is also 1. Okay. So, if you will take only the nucleus of the atom, nucleus of the hydrogen atom, there will be only 1 electron. There will be only 1 proton. So basically, sometimes we give name to proton as hydrogen nucleus. Okay, and representation is this H1 into 1. This is representing charge. I will not say this is a charge. This is atomic number. This is number of protons. This is representing number of nucleons. So there is only one number of neutrons, sorry, number of nucleons. Okay. Okay, this representation I will explain you later. Okay, because if I will tell you now, then you will not get it. For that, we will study what is atomic number, what is mass number, and what is atomic mass. Okay, then we will come back to this, and then we will discuss. Basically, this one is representing the atomic number, and this one is representing the mass number. Okay. Okay. This is the hydrogen atom, and inside the nucleus of hydrogen atom, there is only 1 proton. There is only 1 proton. There is only 1 proton, no neutron. After this, what is neutron? On neutron, the charge is 0, means neutron is neutral. Neutron is neutral. The mass of the neutron is 1.6749 into 10 to the power minus 27 kg. And mass of proton was 1.6726 into 10 to the power minus 27 kg. So when you will compare the mass of proton and neutron, so mass of neutron will be slightly more than that of proton. And these two masses you can consider approximately equal. So if this mass is 1 AMU, approximately this mass will also be 1 AMU. Okay, and this is also represented by 1 mu. Symbol this. The meaning of this and this I will tell you later. With the lecture, you will get to know what is the meaning of this and this. Now, atomic number, mass number, and atomic mass. Atomic number is number of proton in the nucleus. Mass number is the number of protons plus neutrons inside the nucleus. And protons and neutrons are also known as nucleons. So you can write number of nucleons. Now, what is atomic mass? Atomic mass will be the mass of nucleons. Mass of nucleons. Mass of nucleons means mass of protons plus mass of neutrons. and mass of one proton or mass of one neutron is 1 AMU. So somehow if you will calculate the total number of nucleons and if you will multiply it with 1 AMU, you will get the total mass of the nucleus. So number of neutrons multiplied by 1 AMU will be the total atomic mass. That will be the mass of the nucleus. Mass of the atom is mass of the nucleus. We consider mass of the atom as mass of nucleus. We consider the entire mass of the atom is concentrated at the nucleus. One AMU is equal to this 1.67 into 10 to the power 27 kg. For example, this is one element X, okay, and this thing is written. For element, this thing is written. Here is Z, here is A. So what this Z is representing? This Z is representing the atomic number. And this A is representing the mass number. Z is representing the atomic number, A is representing the mass number, and atomic number is equal to number of protons inside the nucleus of this element. Number of protons. And mass number is representing number of nucleons. Nucleon means number of protons plus neutrons inside the nucleus. Okay, so see in this case, this is atomic number, this is mass number. So in this oxygen atom, there will be 8 proton because 8 is the atomic number. How many nucleons will be there? 16 nucleons will be there. And if you will calculate the neutrons, then you will do 16 minus 8 means 8 neutrons. Now chlorine, what is the number of proton in chlorine? Chlorine atom. Hello Fawaz. Hello Fawaz.
Hello, yes, sir.
Hello, how are you?
I'm fine, sir.
Why you were absent from so many classes?
Sir, exam चल रहे थे.
Okay, it's fine, it's fine. So I have started this chapter, nuclei. Okay, so I am telling about what is atomic number, what is mass number, and what is atomic mass of some element. So once again I am telling, atomic number of an element is basically number of proton in the nucleus. Total number of protons in the nucleus is basically the atomic number of the element. Mass number is basically the mass number is a number. So mass number is the number of protons plus neutrons inside the nucleus, because inside the nucleus there are protons and neutrons. So mass number is basically the number of protons plus neutrons. Protons and neutrons are the nucleons. So you can say number of nucleons. Also the mass number. If you will multiply number of nucleons with 1 mu, you will get the atomic mass. Because mass of one nucleon is 1 AMU. If you have 5 nucleons, then what will be the mass? 5 AMU means you will multiply. These are the number of nucleons, and you are multiplying it with 1 AMU. Okay. So basically, it will become A into A AMU. A is O. Thank you. Fawaz, now it's fine.
Ah, yes, sir.
Okay, sorry for that. Okay. So atomic mass is basically the mass number multiplied by 1 AMU. And what is mass number? Mass number is basically number of nucleons. And what are number of nucleons? Total number of protons plus neutrons inside the nucleus. And 1 AMU is equal to this. And if this is the element X, and this is written like this. Here is Z, here is A. So this Z will represent the atomic number and A will represent the mass number. And I told you what is atomic number. Atomic number is equal to number of protons, mass number, number of nucleons. For example, this is the oxygen atom. And in this oxygen atom, we want to calculate the number of protons and number of neutrons. So number of proton will be the atomic number. So this is the atomic number and this is the mass number. This is mass number A and this is atomic number Z. Okay. In some books, you will get oxygen atom, the atomic number and mass number can be written in this form also or in this form also. Okay. So basically, we want to calculate the number of protons in the oxygen atom. So number of protons is equal to Z, means atomic number. And what is the atomic number? 8. Number of nucleons, if I want to calculate number of nucleons, number of nucleons is equal to A, means atomic means mass number, that is equal to 16. Now if someone is saying calculate the number of neutrons, calculate the number of neutrons, so we know that number of proton plus number of neutron inside the nucleus is equal to number of nucleons, that is equal to mass number. So from here we can calculate A minus number of proton, or you can write this as A minus Z also. So number of nucleons can be written as A minus Z. So it will be 16 minus 8. So number of neutrons will be 8. Now come to this question. In this question, we have to find, in this example, Fawaz, now my voice is okay, na? It's fine, na? Or it's
Yes.
breaking?
Like
Not
little
breaking,
bit
yeah?
sometimes. Yes. It is
Sometimes
good.
it is.
Yeah, rarely it is.
Okay. Just a minute, I'm checking. Just wait, both of you. Fawaz, now you will be regular in classes?
Sir, my next exam is on Sunday. Practical exams are going on that. So.
Yeah. Okay, it's fine. Internet speed is fine. I think there is some. Okay. So if there is lagging in my voice, please tell me, Hamza and Fawaz, both of you. So now come to this question. Come to this question. Both of you. Okay. So in some books, this is basically what? This is carbon. Okay. 613. It is written. So what this 6 is representing? Z. And what is Z? Atomic number. What this 13 is representing? A. And what is A? Mass number. Okay. Now we have to find number of protons. So how we will find number of protons? Number of protons is equal to the atomic number. And what is the atomic number? 6. So number of proton becomes 6. Now, what is number of nucleons? Mass number. Number of nucleons, mass number. Mass number is A, and that is equal to 13. Now, if you want to find the number of neutron, so do 13 minus 6. Do 13 minus 6. You will get 7. So you should know what is atomic number, what is mass number, and what is atomic mass. Okay, now isotopes. What are isotopes? Atoms of same element whose nuclei have same number of protons. Same number of proton. Same number of proton means atomic number will be same. Atomic number will be same. But different number of nucleons. Number of nucleons means mass number will be different. Example, this is the example of hydrogen element. So in nature, hydrogen is found in these 3 forms. This is hydrogen atom, this is also hydrogen atom, this is also hydrogen atom. Okay, and these are the isotopes of hydrogen. So in case of hydrogen, what is same? Z is same. So you can see here Z is same. This is Z, this is Z, this is Z. Means atomic number same, and this is mass number different. So these are isotopes. Isotopes have same mass number, same atomic number, different mass number. One more example. Chlorine. You can see 17 and 17. Same atomic number. See mass number 35, 37. Different. So these are isotopes. Isotopes of chlorine. These are the isotopes of hydrogen. Now, in nature, now we will discuss what is the significance of the isotopes. In nature, chlorine atom or chlorine you will find in 2 forms. One form of chlorine atom you will find like this. Another form of chlorine will be like this. Okay. So one form of chlorine will be like this, another form of chlorine will be like this. Okay. Suppose these 2 forms are there. If you want to find the average mass of this chlorine, because you have seen somewhere that chlorine mass is taken as 35.5.
Chlorine mass is taken as 35.5. Why? Because chlorine have two isotopes and we take the average mass of chlorine. Now we will calculate, we will learn how we can calculate the average atomic mass. So now see here, how fractional atomic mass. Fractional atomic mass, and why we are calculating the fractional atomic mass? Because of the isotopes, because different isotopes have different masses, atomic masses. So we will take average. So how you will take average? There is one formula. Average atomic mass is given by A1N1 plus A2N2 plus A3N3 and so on. Now what is A1? A1 is the atomic mass of first isotope. A1 is the atomic mass of first isotope. A2 is the atomic mass of second isotope. If there are three isotopes, then A3 is the atomic mass of third isotope. What is N1, N2 and N3? N1 is the fraction of, okay, N1 is the fraction of the isotope. Okay, fraction of the isotope. N2 is the fraction of isotope 2. N3 is the fraction of isotope number 3. Okay, A1 atomic mass of first isotope, A2 is the atomic mass of second isotope, A3 N1 is the fraction of first isotope, N2 is the fraction of second isotope. This is the chlorine, and this chlorine is having two isotopes. This chlorine is having two isotopes. These are two isotopes. We want to find the average atomic mass. So we will apply this formula. A1N1 plus A2 into N2. What is A1? A1 is the mass of first isotope, that will be 35, and fraction of first isotope. So fraction of first isotope is 75%. In nature, this isotope percentage or this atom of chlorine, you will find 75%, and this atom of chlorine you will find 25%. So this fraction is 75%. So 75 divided by 100 plus this mass 37 multiplied by 25 by 100. When you will calculate this, you will get 35.5 AMU. Isobars. Isobars have same mass number, but different atomic number. So this is the example of isobars. So you can see 6 and 7. So atomic number different and mass number same. This is atomic number Z, this is mass number A. So these are isobars. So these are the atoms of different element having same mass number and different atomic number. This is also, see, different atomic number, same mass number. These are also isobars. After that, there are isotones. Isotones have same number of neutrons. The isotones are the atoms of different element having same number of neutrons. Atoms of different element whose nucleus have same number of neutrons but different number of protons. Okay. So same number of neutrons means A minus Z will be same. Okay. A minus Z is same not nucleon. This will be same number of neutrons. Atomic number will be different, mass number will be different. Now you can see here. This is the example of isotones. Atomic number of lithium is 3. Atomic number of beryllium is 4. So atomic number is different. See the mass number 7 and 8. Mass number is also different. Now number of neutrons. Number of neutrons, how you will calculate? 7 minus 3. 7 minus 3 means 4 neutrons. 8 minus 4. 4 neutrons. Same number of neutrons. So these two atoms are isotones. Understanding, Fawaz, Hamza?
Sir, can you say it again?
Hello, Hamza. Fawaz, are you getting my voice?
Yes, sir.
Have you understood? Are
Yes,
you
I
getting
said,
it?
can you say it again?
I'm saying, are you getting it?
Yes, sir, I am saying, can you explain it again?
Okay. Again, I should explain.
Yes.
Is my voice okay now?
Yes, sir, yes.
Okay. So don't get confused. Okay. Don't get confused. Okay. With the help of element, I will explain.
Sir,
Suppose this
this
is
isotones, can you explain it again?
isotones.
Yes.
Okay. So see, these two are isotones. Okay. So remember one thing for isotones. Isotones will have same number of neutrons. Same neutrons. Okay. Isotones will have same number of neutrons. So we will check. Okay, we don't know whether the lithium and beryllium. This is beryllium, na? Chemistry.
Yes, sir.
So lithium and beryllium, we will check whether these are isotones or not. What is the condition to become isotones? What is the condition that two atoms will be isotones? They will have same number of neutrons. They will have same number of neutrons. Now calculate number of neutrons in lithium and calculate number of neutron in beryllium. This is mass number of lithium. This is atomic number of lithium. This is mass number of beryllium. This is atomic number of beryllium. This is A. Okay, so A is known as mass number and Z is known as atomic number. if you are calculating number of neutrons, so number of neutrons will be mass number minus atomic number, A minus Z. So what is the value of A minus Z for this? Was
4.
yeah, very good. So what is this for?
This is
Number
number
of
of neutrons.
neutrons. So 4 neutrons. N I am representing neutron. Now calculate number of neutrons for this. 8 minus 4?
4.
4 neutrons. So these two atoms means this is the lithium atom, this is the beryllium atom. These two atoms have same neutrons or not?
Yes, sir. Same.
So if same neutrons means these are
Isotopes.
you got it?
Yes, sir.
Hamza, understanding?
Yes, sir.
Okay. This is very easy thing, but you can get confused. I know, means you may get confused, but for that you have to revise it once, then it will be clear. Okay. Now we will see shape, size and density of nucleus. Shape, size and density of nucleus. Okay. So shape of the nucleus we consider spherical. We consider shape of nucleus as sphere. Nucleus is sphere. For all practical purposes, we take nucleus as spherical in shape. But in actual, the nucleus is not a perfect sphere. Basically, there is a deviation. Okay, there is a deviation to be a sphere. But for the calculation purpose, okay, or for the practical purposes means for doing experiment, okay, for if we want to calculate anything, then we will consider nucleus as perfect sphere. So next topic is this. So first we will see what is the shape of the nucleus. So shape of the nucleus is sphere for practical purposes, but there is slight deviation. Okay, for all practical purposes, shape of nucleus is considered as spherical, and there is a slight deviation in the shape, that is approximately, you can say, less than or equal to 10% deviation is there. So in actual, the nucleus is not a perfect sphere, but for calculation purpose, we will take it as sphere. So you can say the shape of the nucleus is sphere. Now size of the nucleus. For calculating the size of the nucleus, if suppose I have given one sphere to you, how you will calculate the size of that sphere? You will calculate either the volume, either the radius. So for finding the size of the nucleus, we will calculate the radius of the nucleus. Okay. So experimentally, it is found that volume of the nucleus, volume of any nucleus, any Any nucleus means nucleus of any element is directly proportional to number of nucleons in nucleus. Now see, volume of nucleus is directly proportional to number of nucleons. Why I have written A? Because A is the mass number and mass number is equal to number of nucleons. So volume we can calculate from here. This is the nucleus and we are considering nucleus as a sphere. So volume of the sphere will be 4/3 pi into r square. R is the radius of the nucleus. So this I can write. I can write this. So mass number is basically representing number of nucleons. Okay. So now see here, from this, we will find the expression for radius. So it will be r cube, and this is directly proportional to 3a divided by 4 pi. Now this 3 is constant, 4 is constant, and pi is also constant. So you will have r cube is directly proportional to a. From here you will get r is directly proportional to a to the power 1/3. But this is mathematics, very easy mathematics of 8th or 10th class. So this is the proportionality sign. So when you will remove this proportionality sign, you will get a constant that is equal to r naught. And this r naught value will be 1.2 into 10 to the power minus 15 meter. And one more thing, 10 to the power 15 meter is equal to 1 Fermi. So you can say this r naught is 1.2 Fermi. Fm means Fermi. And this r naught is constant also for all the nucleus. This is radius of nucleus. This is constant for all nucleus. And what is A? A is the mass number. R is equal to R naught A to the power 1/3. R is equal to R naught A to the power 1/3 is the formula to calculate the radius of any nucleus. You will put A, value of A, you will get radius of different nuclei. So remember this formula. Understanding, Fawaz?
Yes, sir.
Understanding, Hamza? Now this is the size of the nucleus. Size of the nucleus means radius. You are calculating radius or volume. Okay. After that, density of the nucleus to calculate density. And now what is density? Fawaz, can you tell me what is density? What is the formula for density? Any idea? Density is equal to mass upon volume. If we are calculating density of water, if we have water and we want, suppose this is the water in the water, I want to calculate the density of this water. So what I will do, the mass of this water, and I will divide that mass with the volume of this water, and I will get the 10 to the power 3 kg per meter cube density of the water. In the same way, I want to now calculate the density of nucleus. So density of nucleus is mass of nucleus divided by volume of nucleus, and volume of nucleus we already have 4/3 pi r cube, and the value of r also we have. Now you can see here, density of nucleus is also known as nuclear density. Density is equal to mass of nucleus divided by volume of nucleus. So now mass of nucleus, mass number multiplied by 1 AMU. See, atomic mass or mass of nucleus is A into 1 AMU. Okay. So A into 1 AMU divided by volume of nucleus 4/3 pi r cube. Now put this value of R, and this value of R is this. R is equal to R naught A to the power 1/3. So we will put this value here. R naught A to the power 1/3. Now here, from here you will get A into 1 AMU. This is divided by 4/3 pi. You will solve this, you will get R naught cube multiplied by A. This A and A will gone. A and A will be cancelled out here. And you will get 1 AMU divided by this value. And 1 AMU is, what is the value of 1 AMU? 1.67 into 24 minus 27. So you will put this value, and you will put all these values because R naught is also constant. So you will put the value of R naught also. And when you will calculate this, somehow you will get the density of nucleus this. So now here is an interesting thing. What is that interesting thing? Density of nucleus is much larger, very large. See, density of nucleus is 2 into 10 to the power 17 kg per meter cube. If you will compare this density with density of water, so density of water is 10 to the power 3 kg per meter cube, but the density of nucleus 2 into 10 to the power 17. 10 to the power 14 times greater than the density of water. That is why in a small space, as compared to the atom, size of the nucleus is very small, and in that smaller mass, whole mass of the atom is concentrated. That is why the density of nucleus is very large. Now we will solve this question. This is the question from NCERT. Example of NCERT. They are saying find the nuclear density for iron. Means we have to find the nuclear density for iron. Rho is the nuclear density. Given mass of the iron is given 55.85 mu. Mu means AMU. This is given. And mass number is also given. A is the mass number. Mass number is given. Now we can calculate the density. What is the formula for calculating density? Density is equal to mass of iron nucleus divided by volume of iron nucleus mass of iron nucleus is given as 55.85 AMU. Volume of iron nucleus and nucleus size is spherical, so it will be 4/3 pi r cube. And what is the expression for r? R is equal to r naught. R is equal to r naught, a to the power 1/3. Now put the value of r here and put the value of AMU also. In 1 AMU, there is 1.67 into 10 to the power 27. 1.67 into 10 to the power minus 27 kg. So this much AMU will be 55.85 into 1.67 into 10 to the power minus 27 kg, and this is divided by 4/3 pi r is equal to r naught into a to the power 1/3 to the r naught a to the power 1/3, and this whole power will be 3. So what you will get? You will get 55.85 multiplied by 1.67 multiplied by 10 to the power minus 27. This is divided by of course, yes, because why 4/3 pi r cube? Of course, we can take for any nucleus, because what we are considering nucleus as sphere. For our calculation purpose, we will take nucleus as a sphere. For any nucleus, we can take 4/3 pi r cube. Radius will be different. For different nucleus, radius will be different. So it means volume will be different. But formula, you will take the volume of sphere always. V is equal to 4/3 pi r cube. Okay, Bhavas?
Okay, sir.
So this is this. Now here, this is 4/3 pi. From here, this is r naught cube multiplied by a. A to the power 1/3 to the power 3 will be a. Now put all the values. It will be 55.85 multiplied by 1.67 multiplied by 10 to the power minus 27 divided by 4/3. Put the value of pi as 3.14, r naught as 1.2 into 10 to the power minus 15 and cube, and mass number A is given as 56. So finally, you will get density of iron nucleus is 2.2 into 10 to the power 17 kg per meter cube. Hamza, understanding? Hamza, hello. If you have any doubt, any of you means Hamza and Fawad, if you want to ask any question, so you can ask me, no problem. Regarding this question and regarding the topics, you can ask me. Basically, this is not very complex things. These are very easy things. What we are doing, we are just calculating the density. And this is simple mathematics. I will not say this calculation is simple, but this mathematics is simple. Mass energy equivalence. Now this is very interesting concept. According to the Albert Einstein, According to Albert Einstein, in 1905, in his special theory of relativity, he said that if you are giving energy to some mass, if you are giving energy to some object, the mass of that object will increase. For example, this is what? This is object. I can say this as an object. Now I am supplying energy to this object. So according to the Einstein, the energy of this pen should, the mass of this pen should increase. And this was the relation he has given. E is equal to m is equal to E by c square. E is the energy given. C is the speed of the light in vacuum, air, or free space. In 1905, Albert Einstein, in his special theory of relativity, suggested that mass is a form of energy. Mass is a form of energy. Mass is a form of energy. He predicted mass and energy are equivalent. Equivalent means if you are giving energy to the object, then mass of the object will increase. And if some mass will disappear, then energy will release due to disappearing of that mass. And if you are supplying some energy to mass, if you are supplying some energy to object, then the energy of that object will increase. This is m is equal to E by c square. Now, few questions. See, which has more mass, a stationary ball, B, an identical moving ball? According to the Einstein, if you are giving energy E, then this much mass will increase. What is this? This is increase in mass. And what is this? Energy given. So energy can be in any form, either in the form of kinetic energy, potential energy, thermal energy, frictional energy, heat energy, energy given. Okay. So now Fawaz or Hamza, can you tell me the answer of this question? Anyone? At least you should try. At least try this question.
Sir, an identical moving ball.
Very good, Hamza, very good. The reason is because the moving ball will have the kinetic energy and a stationary ball will not have energy.
Speed also include.
Yeah,
So
of course.
gives the hand in
that is also
mass.
right. That is also right. But I am not taking into consideration means when something is moving, the mass will increase. That is different concept. M is equal to m naught under root 1 minus v square by c square. That is different thing. Here we are that is also right. Means that way also you can solve this question. Very good. But we are solving in this way. So basically, this is the stationary ball. This is the stationary ball. So if this is the stationary ball, I will solve this question in this way. You can see here. This is a ball, and this ball is the stationary. So this stationary ball will have some mass. Okay, so suppose m rest is the mass of this stationary ball. Okay, m is the m rest is the means mass at the rest. Now suddenly this ball starts motion. Suddenly this someone has given the kinetic energy. Someone has given the kinetic energy. Oh, not given the kinetic energy, someone has given the energy. So that now this ball starts motion. If this ball starts motion, means this ball will have the kinetic energy. Means this ball, if this ball is moving, means this ball is having the kinetic energy. Okay, so I am removing this, no need of this. Motion, the energy associated with motion is kinetic energy. Okay. Now this ball will have, what is the mass of this ball? This ball will have this mass also, mass at rest. Okay, but this ball is now in motion, and due to the motion there will be the kinetic energy, and due to the energy the mass of this ball will increase. Due to the energy the mass of this ball will increase. Okay, so you can say that mass of the moving ball, is equal to, this ball will have this mass. Now we are calculating mass of this ball, so this ball already have this mass. Very good, so write m rest. Now there is one mass extra due to kinetic energy, and what is this extra mass? Energy divided by c square. And what type of energy this mass have? Kinetic energy divided by c square. So that is why this option will be correct. Now another question. Again you have to apply this formula. M is equal to increase in, M is increase in mass, E is the energy supply divided by c square, and value of c is 3 into 10 to the power 8 meter per second. So they are saying find the increase in mass of 1 kg of water when it absorbs this much of energy. This is a glass, and in this glass suppose 1 kg of water is there. How much water? 1 kg of water is there, and now you are supplying energy of 4.2 into 10 to the power 3 joules of energy you are supplying to this water. What will happen? According to the Einstein, if you will supply energy, mass of this water will increase, and given by this formula. So increase in mass is equal to energy supplying means 4.2 into 10 to the power 3 is divided by 3 into 10 to the power 8, and square of this you will get, I think actually I already did the calculation, that is why I am so you will get 4.7 into 10 to the power minus 14 kg. So this mass is very small. Increase in mass is very small. So that is why in our real life, what happens if something is moving, if we are supplying some energy, so generally the mass we consider remains same. Why? Because if you are supplying energy to something, means this amount of energy also if you are supplying, then only this much amount of mass will be increased for that object. and that mass, this increase in mass is negligible for us. That is why in practical life we don't take into consideration the increase in the mass. But in actual, if you will see at microscopic level or nanoscopic level, then mass will increase. So you can write one statement: this mass is very small, this mass is very small, but not zero. Now this is very famous equation, E is equal to mc square. What is the meaning of this equation? If suppose m mass is disappeared, if suppose m mass is disappeared, then this much of energy will release. If m mass is disappeared, E energy will released. So we will use this equation when we will study mass defect. Next topic, mass defect. Now we will discuss what is mass defect. Basically, what is mass defect? During the formation of nucleus, during the formation of nucleus, what happened? We know that nucleus is made up of protons and neutrons. So when protons and neutrons are combining or binding to form the nucleus, there is a mass defect. What is that mass defect? Basically, before the formation of nucleus, the mass of nucleons will be greater than after the forming. Okay, after the formation of the nucleus. Now in this way we will see mass defect. So what is mass defect? These are the nucleons. Now formation of the nucleus is taking place. Formation of nucleus. So these nucleons are combining to form the nucleus. So basically, this mass, the mass of the nucleons should be equal to the mass of nucleus. Because these nucleons are constituting the nucleus now. So this mass should be equal to this mass. But it is found that mass of nucleons is greater than mass of nucleus. Now where the remaining mass gone? And that remaining gone mass is known as the mass defect. Understanding? Was and Hamza?
Yes, sir. Yes.
So mass defect is basically this. In the formation of the nucleons, some mass is disappeared. That mass is known as the mass defect. And what is the value of mass defect? Because nucleons have more mass than nucleus. So to calculate the mass defect, you will calculate the mass of nucleons minus mass of nucleus. So for the definition, some mass disappears during the formation of nucleus. The mass that disappears is known as the mass defect. Now we will see what is the expression of the mass defect. Suppose this is some element X. This is the mass number, this is the atomic number. What is the mass number? What is the atomic number? Atomic number is basically the number of protons in the nucleus of this element. What are number of neutrons? A minus Z, number of neutrons. So basically what I am saying, in this element Z protons are there, A minus Z neutrons are there. So remember this thing. Z protons are there, A minus Z neutrons are there. And one more thing. Number of nucleons is equal to number of protons plus number of neutrons. Remember this thing. Okay, so if you will calculate the mass of nucleons, means you have to calculate the total mass of the protons and neutrons inside the nucleus. Okay, so what is the mass defect? Mass of nucleons minus mass of nucleus. So mass of nucleons minus mass of nucleus. And what is the mass of nucleons? What is the mass of nucleons? Mass of nucleons is mass of total mass of protons plus neutrons. You can write here, mass of nucleons is mass of protons plus mass of neutrons. Okay. So how you will calculate the mass of, I'm removing this, no need of this. I am just calculating here what is the mass of proton. Mass of proton. So mass of proton will be the mass of total protons inside the nucleus. And how many protons are there? Z protons are there. And 4 Z protons are there now in this nucleus. So for one proton, the mass is MP, means mass of proton. And for Z protons, the mass will be ZMP. So this will be the mass of protons. So mass of proton will be ZMP. And mass of neutron, total number of neutrons A minus Z, total number of neutrons A minus Z multiplied by mass of 1 neutron. And this is mass of X. Mx means mass of nucleus of this X element. So basically this is the final expression for mass defect. Now what I told you, this is the mass defect, means some mass is disappearing in this process. And if some mass will disappearing, if some mass is disappearing, means energy will release. So during the formation of nucleus, energy will release due to the mass defect, and that energy is known as the binding energy. Binding energy. These are nucleons. This is nucleus. So there will be the mass defect. There will be the mass defect. Just told you. Due to that mass defect, this delta E energy will release according to the E is equal to mc square. Yeah, we will solve question. I have questions here. Okay, these are the questions we have. So don't worry, first we will understand.
Okay. Okay.
Without question, I know we cannot understand the concept. According to E is equal to mc square, if there is some mass disappearing, then energy will release. So this energy is releasing and this energy is known as the binding energy. But in books, the definition of the binding energy is given in some different way. How they give the definition. Suppose go in the reverse direction, in this direction. Move in this direction. So to break this nucleus, this much amount of energy you have to give. To separate the nucleons, to separate these nucleons, this much amount of energy you have to give. And that is known as the binding energy. So binding energy is basically the amount of energy given to the nucleus to separate its nucleons. And this delta E is given by delta M into C square, delta M into C square. Delta M is the mass defect. Okay, so delta E is equal to, this is delta M, expression of delta M, and into C square. So what is binding energy now? It is the amount of energy released to separate all nucleons from the nucleus. And what is the significance of the binding energy? Binding energy binds the nucleons inside the nucleus. Okay, so we will solve this question. Okay, Fawaz, see this question. First, read this question. This is the question from NCERT. Similar to the NCERT, you can say. They are asking, find the binding energy associated with mass defect of 1 AMU. Means what is given? Delta M is given as 1 AMU. Okay, and it is given in the question 1 AMU is equal to this much of kg. And they are asking the binding energy. So what is the binding energy? Binding energy is basically the energy released due to the mass defect. So it will be delta M into C square. So what is delta M? Delta M is 1 AMU. C square means 3 into 10 to the power 8 meter per second square. Okay, now convert 1 AMU. So this 1 AMU can be written as this 1.67 into 10 to the power minus.
Sir, C square, right? Square, C square.
Sorry, it will be C square.
Okay.
So now it will become 3 into 10 to the power 8 and square of it. So basically, this is the energy in joule. This is the energy in joule. Okay. There is one relation that you have to remember. In 1 joule, I think there will be 6.4 into 10 to the power 18 electron volt. Fawaz, just check this value. Can you check this? 6 point something, I think 6.3 it will be. 3.4, I think. In
Okay.
1 joule, how many electron volts are there? Just check and tell me, please.
Sir, 6.242 into 10 raised to 18.
$6.242.
Yes.
if you don't know na this value, suppose if you don't know this value, so what you should do na, in 1 electron volt there are 1.6 into 10 to the power minus 19 joules. So now from here also you can calculate in 1 joule there will be 1 upon 1.6 into 10 to the power 19 electron volt. So you will get the same value 6.242 into 10 to the power 18 electron volt. Okay. So from here also you can calculate it. So now basically this value is in joule and we will convert this in electron volt. So it will become 1.67 into 10 to the power minus 27 multiplied by, it will be 3 3s are 9, it will be 10 to the power 16 and multiplied by this value 6.242 into 10 to the power 18. Now this will become in electron volt. And one more thing, now we will convert this electron volt into mega electron volt. So 1 mega electron volt is equal to 10 to the power 6 electron volt. So what we will do, we will multiply this with 10 to the power. From here you can calculate in 1 electron volt there are 10 to the power minus 6 mega electron volt. So here we will have 1.67 into 10 to the power minus 27 into 9 into 10 to the power 16 into 6.242 into 10 to the power 18 into 10 to the power minus 6. So approximately this value will come out to be in mega electron volt. It will be 931.5 mega electron volt. I think this will be the value. Check 931.5 mega electron volt. So now try to analyze if there is a mass defect of 1 AMU, how much energy is releasing? Okay, now note down. Very important point. If mass defect of 1 AMU, then 931.5 electron volt, mega electron volt energy is releasing. Mega electron volt energy releasing. Means for 1 AMU mass defect, energy release is 931.5 mega electron volt. If 2 AMU mass is disappearing, then it will be 2 into 931.5 mega electron volt energy. If 5 AMU mass is disappearing, then how much energy will release? 5 into 931.5 mega electron volt. Okay, so from here we can go to one formula that delta E is equal to delta M into 931.5 and this value will be in mega electron volt and mass defect should be in AMU. So directly you can calculate. If someone is saying there is a mass defect of 0.0005 AMU, then you will put 0.005 AMU and you will multiply with this value, you will get the energy directly in mega electron volt. There is no need to do this much of calculation. Understanding, Pavas? Pavas, understanding?
Yeah, yes, sir. Yes, sir.
So you have to remember this formula. You have to remember this formula. Okay. Suppose I am saying that mass defect is 0.002 AMU. So how much energy will be released? So what you will do? You will not do that question in this way. You will write this formula: delta E is equal to delta M multiplied by 931.5 mega electron volt. Okay, and delta M is 0.002 and multiplied by 931.5, and you will get the answer in mega electron volt. Finish. Now next thing, this is the last topic of this class. Okay, so I will take hardly 10 minutes. Okay, Fawaz? Okay,
Okay.
Hamza? Yeah. So basically this is the last topic of this class. Okay. So basically now we will discuss the nuclear stability and the binding energy per nucleon. First we will read this statement. The binding energy of a heavy hydrogen, this is the heavy hydrogen, is this 1.1 mega electron volt. And binding energy of uranium 238 is this. And binding energy of iron 56 is this. So Fawaz, can you tell me binding energy of this uranium is this, and binding energy of iron is this. Which will be most stable, uranium or iron? The nucleus of iron will be more stable or nucleus of uranium will be more stable?
Iron.
How?
Sir, because less binding energy. Less binding energy.
So less binding energy. What is written here? Stability is directly proportional to binding energy. Means they are saying more will be the binding energy, more will be the stability.
Oh, yes, yes.
So according to that, this should be the answer. But your answer is correct. This relation is not valid. Actually, what happens? Binding energy is not the stability factor. The stability factor is binding energy per nucleon. Think in this way. This is the uranium nucleus. So this uranium as compared to iron, it will have large number of nucleons. Uranium as compared to iron have large number of nucleons. So to bind those nucleons, large amount of binding energy should be required. So, okay, large amount of binding energy will be required. But in case of the, and which is the criteria, means what is, how we can say which is stable, means the maximum amount of binding force or the amount of binding force will be between the nucleons will decide the stability of nucleus. But here the energy is distributed to bind the large number of nucleons, and here is the less energy, and this less energy is distributed in binding the less number of nucleons, because iron have the less number of nucleons. So basically now this iron is most stable. Criteria for the stability is binding energy per nucleon. So basically this is the graph. I took this graph from the NCERT. So now you can see this graph. This graph is between the binding energy per nucleon, and that is in mega electron volt, and between the mass number. 0 mass number, 50, 100, 150, 200, 250. Now you can see for mass number 0 to 50, binding energy per nucleon is increasing. Now from here, from 50 to you can say 238, the binding energy per nucleon is decreasing. And this H2 has the least binding energy, and iron, not the binding energy here. The binding energy per nucleon is increasing till iron, and iron has the maximum binding energy per nucleon. More will be the binding energy per nucleon, most stable will be the nucleus. So iron nucleus is the most stable nucleus among all the elements. So, and this is the least stable because having less binding energy per nucleon, and uranium 238 is having less binding energy per nucleon. From this graph you can see as compared to the iron. So now there are some conclusions I have taken from the graph. So there is no required to learn this graph, just see iron has the maximum binding energy, uranium have this much less than iron the binding energy, and okay. So you should know how, what is the graph, mean what is the shape of the graph, and the conclusion from the graph, from this graph is important. Now we will conclude. Remember, binding energy per nucleon is the stability factor. So now see, from A is equal to 50 to A is equal to 80. So A is equal to 50 to A is equal to 80 means you are moving from here to here. You are moving, 80 will be somewhere here. Somewhere here will be 80. So this is the mass number from 50 to 80. Now you can see from 50 to 80, 50 to 80. Binding energy per nucleon is approximately equal to this. 8.5 mega electron volt. So you can see here in between these, okay, when you will see, suppose you are watching, you want to see the binding energy at 50. So at 50 you will get binding energy more than 8, and here at 80 if you want to find, here also you will get more than 8. So basically from 50 to 80 the average binding energy per nucleon from the graph concluded as 8.5 mega electron volt. So 8.5 mega electron volt means this is the maximum amount of binding energy per nucleon for the mass number 50 to 80. For the elements of mass number 50 to 80, there is a maximum binding energy per nucleon, and stability is depending upon the binding energy per nucleon. So these elements having the mass number 50 to 80 are most stable element. Okay, so these nucleus are stable nucleus. Now second, for iron, now you can see iron has the maximum binding energy per nucleon, so iron is the most stable. So this is written here. So iron have approximately equal to 8.8 mega electron volt binding energy per nucleon, has the highest binding energy, hence most stable. Now for greater than 180, binding energy per nucleon decreases slowly. Now see, greater than 80, when you are moving in the graph from here to here, here the binding energy per nucleon you can see is decreasing slowly. And when you are moving from 80 to 238, you will get larger nucleus. You will get larger nucleus, and binding energy is decreasing. So basically, this come to this nucleus now. Come to this uranium. So what does uranium want? Stability, because binding energy is less. So this uranium wants stability, and this uranium is large. So this uranium, okay, will do nuclear fission or do the radioactivity. So binding energy per nucleon decreases slowly, and for 238 means uranium, it reaches to 7.6 mega electron volt. These heavy nuclei are unstable because from 80 to 238 are the heavy nuclei. Okay, so and these have the less binding energy per nucleon. So they will try to gain stability, and how they will get stability through nuclear fission and through radioactivity also. Last point, A less than 50. So now see, A less than 50 means in this region. See, the graph is decreasing sharply. Means the binding energy per nucleon is decreasing sharply. See this, H2, H3 have very less binding energy per nucleon. So if they have less binding energy per nucleon, means they are less stable. And everyone in this universe means everything in this universe want stability. So these also want stability. So how they will get stability? They will do the fusion reactions. Okay, they will combine so that they should have higher binding energy per nucleon and they will become stable. So this is written for A less than 50, binding energy per nucleon decreases sharply and reaches to 1.1 mega electron volt for S2. Now see, for H2, this is approximately 1.1 mega electron volt here. These nuclei are light nuclei because, as you can see now here, mass number is less. So lighter nuclei will be there. Mass number is less means mass is less, lighter nuclei. So these nuclei are light and unstable. They try to gain stability through nuclear fusion. So in the next class, we will discuss nuclear fission and nuclear fusion. Radioactivity is deleted from your syllabus this time. Okay, Hamza and Fawaz. Now what you should do? It will take 5 minutes. Take the screenshot fast. Just a minute. Okay, Fawaz.
Okay.
Just take the screenshot, both of you. These notes are very, very important for you, remember.
Yes, done, sir.
Hamza, take done.
Yes, sir.
Achha, okay. Now take this.
Yes, done, sir.
Okay. Okay. Take this. Done?
Yeah, yes.
Okay.
Done, sir.
Okay.
Yes, done, sir. Done, sir.
Okay.
Done, sir. Done, sir.
Okay.
I'm done.
Done? Okay.
I'm done, sir.
Okay, very good.
It's done, sir.
Okay. Hamza, you should also take these screenshots.
Done, sir.
Okay.
Yes, done, sir.
Okay.
Done, sir.
Hamza, are you taking the screenshots?
Yes, sir.
But these notes are very important for you. Okay, because I have made these notes by myself, and before these notes there is a lot of hard work. Okay, and for us, when your practicals will over,
Sir,
mhm,
in February first week, maybe. First,
so
yes.
Feb 1st.
Yes.
So now, last class will be the means next class may be the last class. Means last, the meaning of the last class is that the syllabus will be completed because this nuclei chapter is
Semiconductor
90, not 90. I will say 70% is completed, 80% is completed, and now we have 20% of nuclei and 100% of semiconductor. So I will try to finish in one class. So make sure, try to join that class, and after that, if you want, then we can start the revision classes also.
yes, yes, sir.
If you want, then it will be okay. Otherwise, if you want to do the self study, then it's your choice. Okay?
Revision will be going on, right? I will join.
No, this is not the revision. After the next class, the revision will be started. If you want to
Yes.
join that, then you can. Okay.
Okay.
Because
Sir, can
revision,
you scroll down?
because revision is also very important. If reading something is important, but revision is more important, that because if suppose you are reading something, if you are learning something, 100% definitely means 100%, I am sure about that, things will be slipped by your mind always. You have seen that now when I was writing the value of 1 joule. Okay, it will be 6.324 now. To
Uh,
see with me, this is
240.
happening. So what you can think of yours? Okay, so right.
Sir, can you go back?
Okay. Revision is, I will suggest you to take the participate in the revision classes. It will be beneficial for you. And if you think that revision classes is not for you, then it's your choice, no problem.
Sir, can you go back?
Yeah.
Previous.
This one?
Yes, sir.
Okay.
I need
Any?
this is the end. Oh, yeah. Okay.
This is the whole question.
Okay.
This done?
Yes, done. Done.
And make sure all these screenshots should be in a proper order. Otherwise, there will be no use of these notes. Hamza, please take the screenshot. Scroll down.
Yes, yes. Done, sir.
Done.
Yes, done, sir.
Okay. And this mass effect and mass not effect, mass defect and binding energy is very important. And I have tried my best to explain this. Okay, now it is all depending upon you. Okay, how much practice you are doing. Okay, take the screenshot.
Yes, sir. Done.
Hamza, taken the screenshot.
Yes, sir.
Okay. Okay, when we will start the revision classes and if you will participate there, so you can, when you will revise, so at that time you can ask your doubts also. Yes, something is revising. Suppose the chapter number 2 current electricity you are revising. So maybe if there will be doubt, then that doubt we can deal with. Scroll down.
Yes, sir.
Scroll down.
Yes, yes, sir.
Okay.
Done, sir.
Okay. Fine. Do this question. So when you will solve not this type of question, so don't do this like this. Okay. It will take your much time. Do this question with this formula. Delta M 931.5. Okay. Now take the screenshot. And one more thing I want to tell you, during the revision classes, we will solve the questions that has previously appeared in the CBSE board examinations. Okay. So that you should have good idea about the means about how the questions are coming in the exam. Okay. And now you have not enough time. Okay. Whatever you have studied, start revising that. Don't waste your time here and there. Okay.
Sir, if we have to calculate mass defect, then what we have to do?
If you
If they
have to
give
calculate the mass
binding.
defect,
Yes, yes.
so very easy. Mass defect can be calculated in many ways. Suppose someone is saying that, Hamza, you also see, someone is saying that these are the nucleons, neutrons, protons, and neutrons, protons, neutrons, and protons. And suppose there is a formation of nucleus. there is a formation of nucleus. Suppose this nucleus is formed from these nucleons. Okay, and it is given that just a minute. This much amount of energy is releasing. This much amount of mega electron volt energy is releasing in the formation of nucleus. 1863 mega electron volt energy is releasing. Calculate the mass defect. Calculate the mass defect. So what you will do? You will apply this formula. 5 delta E is 1863 mega electron volt, delta M, and this is also in mega electron volt, multiplied by 931.5 mega electron volt. Now what will be delta M? 1863 divided by 931.5, and this is finished, and this is 2 AMU. Understanding?
Yes, yes, sir.
Because in this way you have to calculate. I can only tell you, we can only solve 2 or 3 questions, but try to catch the concept. Okay, whatever will be the question can be, there can be infinite number of questions you can get, but concept will remain, fundamentals will remain same. Fundamental will never change. Okay, so taken the screenshots of this.
Yes, yes, sir.
Okay. Take this.
Yes, sir. Done.
Then take this also.
Yes, sir. Done.
Okay. Now take the screenshot of this.
Yes, done, sir.
Done? Okay, just a minute. Just a minute. Just 1 minute. Done?
Yes, yes, sir. Yes, sir. Done. Done, sir.
Okay. Hamza,
Yes, sir.
better taken all these screenshots. Took all these screenshots. So now what you have to do, revise these notes, okay? Just I will say that only. Revise these notes, okay for us? And now we will meet in the next class, and in the next class we will finish this also, and I will try to finish the semiconductor devices or communication system. I will try to finish that.
Sir, in one class.
That chapter is very, I will try means in one class, because that chapter is not that lengthy like optics and all that. Okay.
Yeah.